I have often heard that constraint programming is not a good technology for solving optimization problems. This is a fake news. Actually, constraint programming is well designed to solve discrete optimization problems as well, and you can optimize any objective function that you want. Let's see how to do that in constraint programming and in how the design is done in MiniCP in particular. Just a few notations first to make sure that we know what we are talking about. A constraint satisfaction problem is a triplet of variables, domains, and constraint. And a constraint optimization problem, in addition to that, defines some objective function that you may want to optimize, that is maximize or minimize. Okay, we assume here that we want to minimize this objective function. So that's a constraint optimization problem. And the goal here is to discover among all the sets of solutions in the constraint satisfaction problem, one solution, the only one, well, at least one solution that minimizes the objective function. Okay, they might, of course, exist more than one optimal solution, but we want to retrieve at least one optimal solution in the constraint optimization problem. How shall we do that? Well, first we will find a first feasible solution. Once we have found a feasible solution, we will say that the next solution that we want to discover is at least as good as the one before. Actually, not at least as good, but strictly better. We want that the next solution that we will find is better, is improving the previous one. And we will continue the solving like that. And at iteration I, there are two possibilities. We find a new feasible solution, and the new feasible solution is better than the previous one because we will enforce with a constraint that it should improve the previous one. Okay, and so by construction, if we find no feasible solution in iteration I, it means that the last solution found at the step before is the global optimum of our problem, is at least one global optimum of our problem. And the process ends when we cannot discover a new feasible solution. Of course, we need in the design of MiniCP to know how to enforce the betterness constraint, how to make sure that we find that the next solution that we discover is better than the previous one. And the drawback of this approach, of course, is that they might be quite deep in the search tree, so you might spend a lot of time to discover the best feasible solution there. So let's consider this process a little bit visually. Okay, so we are exploring a search tree. I have represented on this picture the feasible solutions in green with green nodes. The intermediate nodes, the internal nodes are represented in gray. And when you see a red node, it means that it was a failure. So there is no update of the solution there. And that's the evolution here of the objective function of our problem. And you will see that every time we discover a new solution, we see that it's strictly improving over the previous one. So overall here, since we are performing depth-first search, don't forget that in constraint programming, most of the time we perform depth-first search. The first solution we discover is this one, then is this one, then this one, 4, 5, 6, 7, 8. So that's the solution number 9. And so every time we discover a new solution, we see that the objective function is improving. And the last one that we find is proven to be the best solution to our problem. Of course, we have spent here a little bit of time exploring the search tree for nothing because we have not discovered an improving solution after that. But that was mandatory for the proof of optimality, right? It's only when the search completes ends that you have completely exhausted the number of open nodes of your search tree that you have proven that the last feasible solution was the best solution to our problem because we have always enforced that the next one must be better than the previous one. In terms of implementation, how to use this framework is this way. You need to have an integer variable that corresponds to your objective function, and then you minimize this objective function. So you call the minimize function here on the solver, and what you get here is an objective object, and then you start the depth-first search as you did before. Okay, you can always print the new improving solution with a callback. So you do on solution, and you print the objective function if you want to really capture the improving solution every time a new improving feasible solution is discovered. And then you start effectively the search there. You do optimize, okay, and this optimize of the objective function will start the search for you, the depth first search. In terms of implementation, if we look how it's done internally in MiniCP, we have an interface that's called an objective. And the objective has only one method, it's Tighten. Tighten is supposed to be called whenever you find a feasible solution, and you make sure by calling Tighten that the next one that you find will be improving that one. You see that this interface is completely independent of constraint programming. Okay, there is just one method there. We do not depend on integer variables. We do not depend on any objects related to the constraint programming solver. Then we have the minimize function and the minimize class. And the minimize class has one internal integer variables that correspond to your objective function, and this one implements the objective interface. And what you can see here is the bound here. So it's a minimization problem. So initially we start with plus infinity, but plus infinity does not exist in Java. So we just set this upper bound to the maximum, to the largest integer value of Java. So integer.max value. Every time you call Tighten, the thing that we will do is that we will capture the objective value. So we take max here because we know that the objective is bound at that time. It's fixed to some values. So we take max. So that's the current value of the objective. And we say that the new bound is equal to the value of max. Okay, that's really the value of max. And we do -1 to say that the next one should improve at least by 1 unit. Okay, because it's an integer variable. So we have no fractional improvement that is possible there. So it should improve at least by 1 unit. And the filtering, because we need to enforce that the domain of this variable x never exceeds this upper bound of the objective function. And so we will here set up a callback to say that every time the fixed point algorithm is called, we will simply remove any value of the domain of x that is beyond, that is above, larger than this upper bound that is gradually tightened during the search. This is how optimization is performed in practice in constraint programming. And then, in terms of modeling, how all this objective function is created for you, because you will not necessarily see it, is that when you call here optimize, when you call optimize there, you call it with the objective function that you have. So this might correspond, for instance, to a minimization objective, the one that we have seen before. And every time a new solution is found, we will tighten the objective. So that will be the -1 that we will do on the bound there. Okay, it's every time a new feasible solution is found, we tighten the objective. Okay, and then that's the depth first search. That's the same depth first search as the one that we use for finding all feasible solutions to a CSP. Nothing has changed. So in terms of optimization, that's completely orthogonal to satisfaction problems. We see that we are not really modifying the code of depth first search there. We just have here some hookup, some instrumentation to make sure that we will tighten the objective every time a new feasible solution is found. And we will also make sure that every time the fixed point algorithm executes, we remove all the values beyond the objective, the current best solution found, so the current best bound for this objective variable. And that's it. This is how optimization is done in constraint programming. So let's summarize. We have implemented the minimization mechanism. Okay, that's a very regular depth first search that enumerates all feasible solutions, but with 2 listeners. One listener will tighten the objective function every time a new feasible solution is found, and every time the fixed point is triggered, we will make sure that we will restrict the bound of the objective variable to make sure that it's impossible to find the next feasible solution that is worse than the previous best feasible solution.